Hi everyone, I'm Haidong Zhu from University of Southern California. Today I'm presenting our paper, KAPAR, Category-Based Proposal Analysis for Referring Relationships. First, let's introduce the task of referring relationships. Referring relationships is to localize the subject and object's entity based on a given query. We plot an example here to show the difference between the detection problem and referring relationships. The two examples on the first row are the detection results for category person and bags. Detection results may have more than one output since there might be multiple person or bags there. To distinguish different people or bags, we need to localize the specific objects given some corresponding descriptions, such as the person with a phone or the bag next to the person. We show these two results on the second row by showing the corresponding localization results for subject and objects in the query respectively. Finding the object in the image that satisfies such kind of relationship query is known as referring relationships. Specifically, in the referring relationships problem, we have a query triplet in the form of subject, predicate, object as input, and the output the localization result for the subject and object entity. We generate the bounding boxes for both subject and object and use these bounding boxes as our final output. There's little previous work directly related with the referring relationships. For the most related method, SSAS, it focuses on generating the heat map based on the attention for subject and object separately. This method applies the predicate as a shift and generates such shift between the object and subject iteratively before generating the final heat map for subject and object entity. Such results are feasible for generating corresponding relationships, but SSAS also has many problems. Since it takes all the subjects into consideration, most of the objects that do not belong to the category of the subject or object will still be taken extra time for evaluation. Also, the heavy computation of heat map makes the resolution for SSAS to be low, which in fact reduces the accuracy of the final referring relationships result. We propose a proposal-based method which is called KAPAR to solve such problem. The KAPAR system consists of two different modules, one for generating the candidates for those proposals that is in the same category as input, subject, and object, which is called the category-based proposal generation module, and another module, which is called the predicate analysis module, is to evaluate the predicate information between the candidate object and subject to figure out which pair should be the most suitable for the given predicate triplet. We first focus on the category-based proposal generation. The category-based proposal generation module generates the proposals based on the category names of the entities enclosed in the bounding box. It first generates the proposal candidates for subject and object respectively. For all bounding boxes generated, it ranks the proposals based on the language embeddings for the category name of the subject and object respectively, and then selects the top K proposals as the detection result. In our experiment, K is set to be 5 for both subject and object. After category-based proposals generation, we can greatly reduce the computational complexity by reducing the number of candidate proposals. We will describe our method more detailedly in the following few slides. For the category-based proposal generation, the first step is to generate the proposals candidates. We apply the RPN initialized with an VGG16 that is pre-trained on the ImageNet and fine-tune it on our dataset. We set NMS in RPN as 0.6 and generate 300 proposals for each image after RPN to feed it into the category-based proposal generating network. All the proposals are extracted the feature vector with a ResNet 50 network pre-trained on the ImageNet for future processing. In the meantime, we extract the language embedding for the noun phrases of subject and objects. The noun phrases are the single words for the category name, which is processed by GloVe embedding system with 300 dimension vector as output. After the language and visual features vectors are extracted, we concatenated the language embeddings with every visual embeddings from the proposals to rank all the visual proposals according to their category names. The score will be evaluated with an MLP and ranked all the bounding boxes for the subject and objects separately. After every bounding boxes are scored, we select the top K proposals according to the scores from highest to the lowest. At this step, we have an output for subject and object score respectively for every entity in the image. So after these, we already have a result for every proposal in the image according to their names about whether they are the subject or the object described in the query. Since we only extracted 5 objects for evaluation, the overall combination is only 25. This greatly reduces the complexity of computation for the second stage. In the second stage, we evaluated every subject-object pairs with the predicate analysis module. Since different from the first stage, where every subject and object are taken into consideration separately, in this stage, we combine the subject and object together to evaluate the score for the predicate relationships between them. So the first step of the predicate analysis is to evaluate the pairwise subject-object that is generated by the previous module. For predicate analysis, instead of using the feature vector, we use the 7x7 feature extracted from the ROI pooling layer from the RPN network, instead of any type of combination of feature vectors. Compared with using the feature vectors, ROI pooling feature both preserve the localization information as well as the appearance information. Moreover, it still keeps the combination between the location and the appearance of different parts in the enclosed bounding box. This greatly helps for the final accuracy for predicate analysis. We made a Appalachian study for evaluating the benefits of using such feature instead of feature vectors in the results part, which we will introduce later. With the two concatenated features, we applied the predicate classifications for every subject-object pairs we extracted from the category-based proposal generation module. We apply a predicate predictor for every predicate so that we can extract another score for the classification about the score for every pair. This score can be seen as the predicate score. So after this step, we have 3 scores: subject score, object score, and the predicate score. For the final prediction, we evaluate the score for the production of these 3 numbers and get the subject and object bounding boxes with the highest numbers as our final prediction. We evaluated our results on 2 public datasets, VRD dataset and VG dataset. Both of these 2 datasets have the form of subject predicate object queries, and we both use top 70 frequent predicates. Detailed descriptions about these 2 datasets are available in the paper. We show our results here in the following slides. We first show that the results for the subject and object IOU for both of these 2 datasets. From the table we can see that we have comparable results on the subgroup category on the VG dataset, and we outperformed all other splits comparing with all our 4 other baselines. Besides IOU, we also evaluate the recall on both 2 datasets. The recall is defined as having the IOU of the predicted boxes and the ground truth boxes greater than 0.5. We show the results for VRD dataset first. Note that since SSAS only generates the heat map, we can only evaluate the top 1 boxes that generated by this method. Our method outperforms all other methods on both subject and object. We also evaluated the score for our 2 different modules variations, KAPAR CP and KAPAR PA. KAPAR CP is the result for the category proposal generation, which can be known as a score for subject and object. And KAPAR PA is the result for the predicate analysis, which is a score for the predicate. We found out that even without any predicate analysis, simple result from KAPAR CP still outperforms the SSAS. This shows that even without any predicate analysis, the proposal generation result is much better compared with heat map. Also, results for simple predicate analysis is higher compared with heat map analysis. This means that with fewer candidate proposals, we can reduce more confusion for predicate analysis. Moreover, we found that combining the score for category-based proposal generation and the predicate analysis, we can have the best result among the all variations. Having both category information and predicate analysis, we can have a better result for referring relationships. We also made a comparison on the VG dataset. Note that since VRD do not provide result for VG dataset in their code, we only made a comparison between SSAS and two modules for KAPAR. We still shows that we have a better result comparing either module with SSAS, and the best result when we combine the two modules together for localizing the subject and objects according to their query triplet. For a population study, we evaluate whether the detection bounding boxes is good enough for predicate analysis. We made a comparison between the top 1 and top 5 boxes for ground truth and our detection result. The evaluation metric is the predicate recall from the predicate analysis module. We found out that the recall for detection is pretty similar, as only using the ground truth bounding boxes for predicate analysis. We also showed that compared with only using the highest score boxes for predicate analysis, top 5 has a recall over 90% for both detection results and ground truth, which means that by only using the top 5 candidates, our method can greatly reduce the time complexity while not do great harm to the final accuracy. For the feature selection, we also made a comparison between different choices of feature embeddings for predicate analysis. We made 4 types of embeddings that can be concatenated pairwise: ROI pooling feature, phrase vector, visual vector, and 5D location vector. We made a comparison between using the ROI pooling feature and the different types of concatenation of feature vectors. We found out that using the ROI pooling feature has the better recall score compared with other combinations. Compared with single visual feature vector or 5D location feature, the results from the ROI pooling layer has both visual feature and location feature, which provides richer information for predicate analysis. We show some visualization results here. All these 4 examples shows the pretty good referring relationships results. Take the last image as an example. We would like to ground a person with a hat. There are several people in the image, and for referring relationships, we like to ground a specific one. Using the predicate analysis method, successfully localize the specific man that is with a hat, which is the man we really want in this image. So this is all for our presentation, and thank you very much for listening.